Welcome back to the deep dive. Today we're looking behind the curtain, the mathematical curtain of reality, I suppose. We're tackling ghosts in physics.
Right. And just to be clear up front, we're not talking about spooky apparitions.
No, definitely not. We mean these, well, necessary but unphysical states, ghost fields that pop up in quantum field theory, QFT.
Exactly. They're mathematical constructs, really.
Right.
You often introduce them when your description of a field is, let's say, a bit too rich for physical reality.
Too rich. How so?
Take the photon. We often use four components to describe it mathematically, but physically. Light in a vacuum only has two polarizations, 2 degrees of freedom.
Ah, okay. So the math gives you 4, but nature only uses 2. A mismatch.
Precisely. And that mathematical overdescription is common in what we call gauge theories. It creates problems with keeping the theory consistent.
So you need something to clean up those extra unphysical bits while keeping the core symmetries intact.
That's the key.
Yeah.
Gauge invariance of symmetry has to be preserved. So we introduce these ghosts. They're artifacts, yes, but they perform this crucial internal mathematical cleanup.
Okay, so our mission today, for you listening, is to sort these out. Understand they're just helpful mathematical tricks, and when they signal something, well, fundamentally wrong with a theory, the good versus the bad ghosts.
Right. And the good ghosts, perhaps surprisingly, are actually essential tools. They're virtual particles, often used for what we call regularization. The most famous are the Faddeev Popov ghosts.
Faddeev Popov sounds quite technical. What's their main job, in simple terms?
Well, they're absolutely required if you want to properly quantize certain complex theories, think non-abelian gauge theories like the one describing the strong nuclear force.
Okay.
Think of them as internal consistency checkers built into the mathematics. They're these rather strange anti-commuting fields. They behave differently than normal numbers, and they act like virtual erasers. Yeah, they cancel out the contributions from those unphysical variables that just naturally arise because of the theory's symmetries. They make sure the final answer only involves things that can actually happen physically.
Fascinating. Okay, what about other good scenarios? I've heard Goldstone bosons sometimes get called ghosts, especially with the Higgs mechanism.
Ah, yes, that's another really interesting case. In the theory of electroweak symmetry breaking the Higgs mechanism, you start with what would be 3 Goldstone bosons if the symmetry breaking were global.
Would be.
Right, but because the electroweak theory is a gauge theory, these aren't independent particles. Instead, they get sort of eaten or absorbed by the W and Z bosons.
Eaten? That sounds dramatic.
It is, in a way.
Yeah.
This absorption is precisely what gives the W and Z bosons their mass. And crucially, it gives them their third polarization state, the longitudinal one, which massive vector particles need, but massless ones like the photon don't have.
So these ghosts become part of the massive particles we actually observe. Very clever.
It's a neat mechanism, yes. Ensures consistency.
Okay, so those are the helpful ghosts, the mathematical necessities. But you mentioned bad ghosts. What happens when a ghost isn't just a tool, but a sign of, well, disaster?
Bad ghosts are genuinely problematic. They typically represent states with a negative norm, which messes up probabilities, or fields with the wrong sign on their kinetic term in the Lagrangian.
Wrong sign kinetic term. Negative norm. What does that mean practically?
A negative norm state leads to probabilities less than 0 or greater than 1, which is, well, physically impossible. It breaks unitarity, a cornerstone of quantum mechanics. It basically means the theory is predicting nonsense.
Negative probability. That just sounds fundamentally broken. The math falls apart.
Completely. And the wrong sign kinetic term.
Yeah.
That often signals instability. Think of kinetic energy of motion. Flipping its sign implies some very strange behavior. It often leads to a causality.
A causality, meaning cause and effect get mixed up.
Essentially, yes. Theories with these kinds of ghosts often don't have a well-defined Hamiltonian, the thing that governs time evolution. It can lead to scenarios where information could, in principle, travel faster than light.
Which brings us to things like the speculative ghost condensate theory.
Exactly. That's a model that deliberately includes a field with a negative kinetic term, exploring potential cosmological implications. But it runs right into these deep problems.
It's like superluminal propagation, things going faster than light.
That's one of the theoretical consequences, yes. Major issues with causality and stability plague such models. They're very difficult to reconcile with established physics.
So, wrapping this up for you, our listener, these ghosts, good or bad, really show the incredible, sometimes counterintuitive mathematical framework needed to make our descriptions of reality work.
They do. It highlights how physicists strive for consistency above all. Introduce a bad ghost, and fundamental principles like unitarity or causality are immediately threatened.
It's a constant balancing act.
It is. And it makes you really think about why the universe seems to obey these rules so strictly. Why is causality so fundamental? Why must probabilities behave? These ghost fields, even the problematic ones, force us to confront those deep questions.